We're back. We successfully lost like more than half of the class immediately. Is it the fact that we have a live stream, or is it the fact that I mean, maybe it's snowing, maybe people just okay, whatever. Uh, yeah, I know it was hard for me too. So, but yeah, I hope we can. Yeah, no, on the way here it was scary. Yesterday, my car, I have a four-wheel drive, but not a very good one, and it was refusing to go up the driveway into my house. So that was scary. But let's what I wanted to say. Yeah, let's still try to show up, and we'll start this participation kind of next week. So even if you live, you have to still to answer the questions to get it right, and you have to answer them live. But today, our plan is to start talking about what is operating system, what it is really about, right? So what does it mean to build one? So, and it still will be a little bit high level because it's okay, introduction, right? But it's okay, we can take it slow because we have enough time. A couple of things I wanted to share before we even start. What do we have here? Wanted to show you that we have Canvas, Piazza, stuff like that, right? So get there, structure. So we have, I merged undergrad and grad version of the class, right? So it has links to everything. It has a link to live stream here, which you can watch. Has a link to the web page, obviously, right? Has a sign up link on Piazza, and you can either access it here from the web page, or you can just go to the same Piazza and like separately just enter your password and stuff like that. So the action item as of today is to just sign up on Piazza. I mean, you can do it later, but it makes sense to start asking questions, right? So someone is advertising a Discord server, somehow computer science, I mean, university, I guess, overall is against using the Discord. So, I mean, it's fine for you. They will go after me, I guess, but we'll see how it goes. So I will be there on Piazza. So I promise to read the messages I receive real-time notifications. I will try to answer, and I'll ask TAs to work with Piazza as well, right? So any questions about the class, or if I forgot something, like some common thing which everyone else does in the class and I suddenly didn't do it? So what was that? Any comments on that? So for now, all good? Okay, and yeah, let me know so we can add new tools and stuff like that. So it's all open. Okay, so back to this introduction lecture, right? So again, so if I ask you a question, and imagine we're not talking about like some abstract book, but imagine we have a startup idea, right? And we want to build it, show it to our investors. I don't know, maybe we have investors, maybe have buddies who can fund us. Maybe we have to go seriously fund for money. This project requires building an operating system. And just to put it in perspective, let me just show you one startup idea. So we all live in Utah. The sun is harsh, in the summer, even in the winter if you go skiing. And we say, look, let's come up with this wearable device, which in this specific picture, it's my daughter wearing it here on her wrist. It's a mock-up, obviously doesn't work. But the idea is you're going to wear this device on your wrist, for example, and if you go swimming, you apply the same amount of sunscreen, and after maybe an hour or two, it says, okay, good, like, you have a danger of being sunburned because I measured your exposure and I start buzzing saying, okay, look, like really, it's either time to go into the shady place or put more sunscreen, right? So kind of makes sense to some degree, right? If you search, you will find similar devices on the market, right? So to some degree similar. And you say, okay, look, how can I build it? Okay, so who can tell me, how can we build this device? What's your action item number one? Like, especially electrical engineering people know the answers, obviously. Okay, go ahead. Yeah. Yeah, for example.
You need a UV sensor.
You need a UV sensor. So, and what do we do? Again, you say, okay, let's Google, and we find this UV sensor, right? So my slides are in slightly different order. So, but actually, yeah, that's what I did. I went online and I thought, okay, let me look up a UV sensor, and I found one. But you also need some kind of a CPU which is going to run this sensor, right? Because sensors usually, like, there might be some digital logic on them, like there usually is, right? So maybe even some firmware, but maybe not. And so what you do a similar step and say, look, what is that? What will be my main platform? And so in this specific project, I said, okay, I'm going to go online and I find something. And I found this Arduino board, which is called Flora. It was a couple of years ago, so back then it was totally a reasonable device. So run some wimpy CPU, right? But imagine you said you did the same steps and said, okay, it's actually quite tiny. So, I mean, it's not tiny for the purposes of this wearable device, but it's tiny for the initial step of prototyping, right? So, okay, you find this board. There is some kind of a CPU here. You say, okay, well, we're going to run something on it, right? And in my specific case, obviously, I took a shortcut and I ran Arduino software stack. But for the purposes of this exercise, let's just imagine that we want to build our own operating system to run it, right? So, and at this point, okay, we have enough context. Like, it's totally like we want to build it. It can be something else. You might say, okay, I want a startup which does whatever security monitoring, and you're going to build a security camera which will alert you when someone comes, right? But we have a ton of those devices today. But maybe it's a drone flying and something, right? So if I ask you a question, and the reason I do that, because I want you to think about operating system as of something what is useful, really, has tangible purpose, right? Versus like you open the book and say, well, a process, not so much fun, right? Okay, so the question number one, imagine we decided about the, like, we set on the hardware, we have a sensor. I also got a humidity sensor just because you have to measure humidity because it somehow affects your exposure. And the question now is how will you able to run anything on this board? So what will be your steps? And this is related to the question how to build an operating system. So what's the step number one? Say again? To power it on. I agree. So you say, look, in order to run something, I should really know what will be the boot protocol, right? So how does this board really let's step backward a little bit. So really, if you want to run something on the board, you want to write a program, something kind of like a main, right? Which this annotation tool is a little weird. So some kind of a program, right? And you say, I'm going to use a compiler. And normally when you use a compiler, it actually sucks a ton of other libraries inside, right? libc, memory allocators, like probably part of libc. So libc itself will have like functions like printf, create a thread, stuff like that. You say, look, most likely that's not going to work. So why will it not going to work in this case? Exactly. So what you said, you said two things. First, it is compiled for different architecture, but imagine we figured out a compiler which can recompile the libc for our architecture. Imagine, for the sake of argument, it's RISC or ARM, something like, or x86, something really familiar, not something exotic. But real reason is that you cannot use libc because you don't have operating system kernel which has system calls, which libc needs to implement even malloc, right? It will request memory from the kernel to implement the memory allocator, right? So you say, look, but still, who knows that you can actually trick the compiler to say, look, please compile me this main file in such a manner that it will run in an environment which I call bare metal, in which there is no libc or anything else. So who knows the trick?
The instruction set.
Say again?
The instruction set.
The instruction set. So the instruction set defines what gets generated. So let me again, I don't see my mouse pointer, unfortunately. So, but essentially, if you generate, like say, some kind of an executable or object file, this instructions here, they can be either x86 or ARM. You can pass a compiler flag. But really what I wanted to say is that there is a way to tell compiler, do not take libc in, just compile and maybe link. Link means make sure that all the references in the program, like pointers or references to global variables, are compiled and linked in such a manner that they are start at fixed address. Let's say at address 0, right? And then if you just copy this, whatever you got out of the compiler, if you copy it at address 0 and you follow some boot protocol, maybe the boot protocol says, I will jump not to address 0, but to some other address. Then you just relink and say, look, my program will be at this other address. Then there is a chance that if you copy this thing in memory of that board, it will actually run. So does anyone ever did anything like that? No. So like even engineering students and no embedded system, nothing. But it's okay. So we're going to do it for x86. So essentially, we're going to boot in x86. But at a high level, what I wanted to say is that I said, like, this is how it kind of works, right? So your step number one, you say, look, my goal is to, like I say, we call it boot into main, right? Or typically you say, well, let's put hello world inside main, right? So it prints something on a screen, which, okay, printing is yet another task, but at least get into main. Sometimes with my students, we don't even have a luxury of a printf, so we just put a value into a register, like put 1 into, let's say, x86 register EAX or something like that, right? But at some point, this is the main kind of idea. Okay, you agree with that? So compilers will do the job. If you read the specification of the CPU and how it boots, you say, look, if I put this piece in memory at a specific address, I will most likely get my program running, right? Okay. Let's just again take a little bit of a detour, and I want to just make sure that we are all on board on how CPUs work, because we all know languages. You know languages better than I do at this point, right? So programming languages, and any other probably as well, real. But what I wanted to say is that we understand that we can compile stuff and somehow it always run. But I wanted to make sure that we understand that how machine works. Machine is actually, the CPU itself is relatively simple as well. So who can tell me how it works? So what's the main kind of thing which CPU does? Good. No. Anyone else?
You read some command from memory, you execute it, and then you to the next step.
Exactly, right. So this is what I actually wanted to remind. So this is as simple as there is a special register on the CPU, which is called instruction pointer, which holds an address in memory from which the CPU reads an instruction, understand what instruction is supposed to do, does something, and just moves to the next instruction, right? And there are loops. Those are jumps, like essentially updates to this instruction pointer and stuff like that. But that's what I wanted to explain here. So just a step back. So again, x86 CPU, when we talk about buying a laptop or a server or a desktop with a specific CPU, we're talking about this, right? So we say, look, this is the thing which we're gonna get online, or maybe the laptop vendor will put it in for us, right? But it's one CPU, right, in our terminology. Today, in modern systems, it has multiple cores, right? So those are like, this is a picture with 4 cores, right? And sometimes today, a core uses multiple logical threads of execution. So it's essentially can context switch in a transparent manner between executing 2 instruction streams, right? So it's called hyperthreading, right? But it doesn't matter for this example, but just to introduce the terminology, right? And Intel calls the CPU a socket, I think, or a processor package or something. It calls cores, and hyperthreading, those are called logical threads. And terminology might vary a little, so feel free to ask me. And it's, again, in our case, we typically will stay on a single core. Actually, later in the class, when we get to concurrency, there will be like multiple cores, right? One CPU, essentially. Okay, cool. And the CPU is attached to memory, as you mentioned. And it seems, okay, what are you talking about? Like, we know it, right? It's a little bit unusual because you never think about it, but there are multiple ways to build CPUs, right? And somehow this way won, right? So this is the way where the program sits in memory and the register just fetch program from memory, but it doesn't have to be this way, right? There's just one way to build it, right? Right? And so, okay, memory is very simple. So essentially it has just two operations. You can write into it, into a specific address, and you can read from it, right? So again, not a lot of magic. But what is most interesting for us today is this CPU execution loop, right? So at a high level, it's very, very simple. So there is this magic register, which is called instruction pointer. So it's here, right? On Intel, it's called RIT. R stands for like 64-bit version of this register. And what the CPU, and it holds a value, like, which is an address of instruction which CPU will execute next, right? And so what it does, it says, okay, look, I will look at whether I really have to execute this instruction, or maybe something bad happened, like exception, something like division by 0 happened and something went wrong. Or in general, maybe like, something like, in this specific case, like you're just talking about exceptions. And assuming that exception didn't happen, you just fetch this instruction. So essentially, the CPU internally, and if you were in this architecture classes, right? So you say, look, I know how to build the RISC CPU, which does it. So essentially what it does is it just reads this instruction from memory, right? This is memory. And this is silicon, right? And there is a connection between them. It's a bus, right? So, but internally, it's reasonably complicated. At a high level, it just reads some amount of bytes, let's say 8 bytes or a cache line, right, which is 64 bytes. So the next step, the CPU says, okay, I will take a look at what I read, like this value from memory, and I will understand that it's an addition instruction, right? Then like there is an internal step which reads something from registers and then executes, let's say, addition, right? So it says I read values from, let's say, RDX and RIX, or whatever maybe I got it wrong with the encoding, but let's say I read value from RIX, I read value from RBX, the two registers, and I will add them internally and put the result inside the register RDX, right? So that means execute instruction. And then if no exception happened, the results are internally committed because, maybe you were executing instructions out of order, stuff like that. Again, it's not the part of our class, but the high level is this. And you say, well, maybe it was an instruction which updates the instruction pointer itself. Maybe it was a jump to a different address, right? Maybe not. Maybe like in our case, it was just addition. And the CPU moves on and says, well, I will increment the instruction pointer by some value, by the size of this instruction which I executed, and I will move to the next instruction. And that's roughly it. So it's a very kind of flat system, right? So it executes instruction by instruction by instruction, right? Very simple. So when you compile your code, why is it important in this class? Because every time you're gonna program something, you're programming against this piece of hardware. So you need to understand how it works, how it behaves, right? And the general mode of operation, one instruction, the next instruction, and so on, right? Okay, good. Reasonably easy. So, and it boils down to just executing one instruction after another. At this point, again, I will ask you a question. So you already have this main, which you compiled. You can load it in memory, right? Magic, it actually starts executing. The first instruction of your main function is actually gets executed by this CPU. If I ask you a question, what is an operating system? What do we really want from operating system? Correct, right. So bare metal means what I just explained. It's just this loop. There is nothing else. Some instructions, like you say, typically when you run a C program, when you compile it, in order to execute it, unless you're very, very careful about it, you need something what is called a stack. So who knows why do we need a stack? And what is a stack?
Like keeps track.
Correct. So, and I will explain it later in the class. We're gonna go through a calling convention. I will explain why we need a stack. But at a high level, stack allows you, stack is a memory which is used for local variables. So imagine you have a function foo, and it has a local variable integer a. And imagine foo does something on this a and recursively invokes itself, right? So this new invocation of foo needs a new instance of a, right? And the question is where like, because maybe first instance has value 0, the second will get 1, the third one will get 2, right? The question is, where do you get this memory? And so this memory is allocated in a form of a stack, right? A region of memory which just grows up and down depending on whether you want to allocate or deallocate memory, right? And so as you say, in this bare metal environment, as I said, like no one will set this stack pointer, and the stack pointer is a pointer which points to the current position in memory where the stack is, right? And you have to take care of it. As we will see when we will start booting into main, our boot sequence will be designed in such a manner that maybe it doesn't even need a stack, just doesn't use a stack pointer. But when we jump into main, we will say, okay, let's put a stack pointer to some value in memory. So you have to take care of it yourself. And then later on, and yeah, operating system, every time it creates a process, it will take care of this. Kind of like we'll set up a runtime environment for the language, because C is a very simple language. It assumes very minimal runtime, but it assumes that there is a stack, valid stack, right? Any other comments? Like you said, okay, we need a stack. That's a good observation. Operating system has to set up the stack, and I will abstract it saying that it needs to set up a runtime environment for execution of the main program. What else do we need from it?
The program will run to completion. Figure out how to run more programs.
Right, correct. So what you said, that maybe we want to run multiple things. In terms of our example, this wearable device, right? We have 2 sensors. And we say, look, maybe we want to read them periodically, read the UV sensor, read the humidity sensor, and maybe do something on it. Maybe even print something on a screen if we have a screen, right? You say, you can do it Arduino style. Do you guys have experience programming Arduino? So do you remember me? I also have very minimal. But Arduino does it as like this. It really it says, okay, here's your main, here's your loop. Do whatever you want. In that loop, you can pull the sensors. You say, look, in this instruction of a loop, I will pull humidity. Later on, I will pull whatever I have, UV sensor. It is okay for small Arduino programs, but when does it go wrong? With this execution model of polling something in a loop constantly. I mean, game engines do the same probably, right? There is the game execution loop. Okay.
It's hard on Arduino to respond to input because you're always in the loop, so it's hard to do something when someone presses the button.
Correct. You also had a comment.
It's hard for the Arduino to switch to another process or interrupts.
Correct. So what it means that in this loop-like model, you say, what if I want to run logically 2 different things? Maybe one shows something on a screen, like a movie, for example. Just it's an exaggeration in this case, but maybe we show some small movies, right? And another one is still reading the sensors in the background. Those are 2 different things, right? And you say, look, can I somehow compose them together on this platform? Meaning that I will write 2 different main functions for them. They are completely different. They don't know anything about it, right? About each other. But I somehow want to run them on this device, right? So it's called time sharing. And for that, the operating system will be context switching from one process to another. It's kind of like time sharing, car sharing service, we have a car and I come and I pay and I use it for some time. And then you come and pay and use it for some time. And maybe it feels to both of us as we each have a car, because unless we have a conflict with time or whatever deadlines, we are probably totally happy about it, right? And so a operating system will do something similar. So this time sharing, switching between two completely different programs and pretending that they both run at the same time. Or they really never do, because you run one, then switch to another, run another, and then switch back to the first one, right? So that's, and again, as I said, Arduino, I think it doesn't even have this. I think Arduino, and I mean, maybe I'm wrong because I don't have enough experience with Arduino, but I don't think it has a process, a notion of context switching, at least the one which I used. So you really have one loop and go for it. Like, if you want to show a movie, do it yourself. Like maybe show 5 frames, then read a sensor, then come back and show another 5 frames of the movie, and do it fast enough so it looks like it's really running, right? So this is the thing, right? So what else? What else do we want?
How is the program?
Right. So, and like, exactly. So what you're saying is that, how do you even access a sensor? So probably there are some buses involved, some signals, low-level stuff. Maybe people who built the sensor knew about them. You as a developer, well, you prefer to have a higher level interface, kind of like read a value and just want a value back. And this software stack, which abstracts the hardware for you, is called, in an operating system terminology, it's called a device driver. In practice, it's kind of like a library, which like knows something about low-level details of something and exposes a higher level interface. But we want this collection of device drivers, so we don't have to deal with every piece of hardware. And maybe, you know, like tomorrow we're going to move from this Arduino board to something cheaper, smaller, and we don't want to rewrite the whole code. We just will rewrite this library, this device driver, and we will get the value back, right? On a completely different sensor from a completely different manufacturer, right? So abstraction of the hardware, right? And that's pretty good. Like, and we will, like, couple of other things which you guys typically know about operating systems, which you didn't name.
Just the point you mentioned, power management.
Power management, yeah, that's hard. Actually, it's actually harder than it seems. But power management, I don't want to talk about it. But yeah, there is. I wanted something simpler. Yeah. Exception handling. So why do we need exception handling? Who can tell me?
Things like one example that everybody's seen see every single day is like segmentation, accessing memory.
Right. So exceptions, I agree with that. I wanna take a slightly different take on exceptions. So the very first exception which we need is and I will talk about it in a second. It's an exception from a timer, because imagine again, my case in which I want to show a movie and still read a sensor periodically. In terms of a car driving, it's kind of critical, because, you know, if you don't read a sensor and don't, you know, the software which maybe adjusts the steering wheel or something, or brakes, will not get a chance to get executed. It's a dangerous situation, right? So a timer interrupt will allow you to say, look, I will allow the movie streaming application or showing whatever playing application to run for, let's say, some number of milliseconds. And then I need a special exception from a timer to give me a chance to make a decision whether I want to run something else or continue with a movie or maybe read a sensor, right? And you mentioned that we want exceptions for isolation, essentially making sure that one program cannot access memory of another program. So I will get to it. It's easier to explain, let's say, like in 5-10 minutes into the class. But you're right. So we need to handle exceptions, and I will get to it. But I wanted to say something. When I was, again, your age, probably, I started working part-time for a security company, which was implementing actually digital rights management. So essentially you have a device, you plug it into your computer, you can watch a movie, because the movie engine essentially encrypts all the media frames and periodically ask for a key from that device. And the device which we got didn't have a file system. It says, okay, I have storage, kind of like memory, permanent storage, like flash, think of it as flash. But there is no file system. So you can say, I'm going to write into address 0 on this device, like maybe it's my key. and I can read from address 0. But then the moment you have multiple keys, you can save names and stuff. Then you say, look, you have to somehow figure out which addresses are taken, which are not taken in this permanent storage. And we had to build a tiny file system for this device. And a file system abstracts like raw storage, which is like byte number 0, byte number 512, byte number 1024 in terms of names. And you can say, look, name foobar.txt is actually located in those storage blocks. And it's surprisingly powerful, right? Everything what we, I mean, actually computers are moving away from file systems, right? So now you have, like when you take a mobile app, in the best case, there will be a search and maybe some kind of a tag, right? So they don't even let you organize your stuff as files, folders, right? So, but like a good example is GitHub. Well, there is no recursion in the project, right? So you cannot have folders, right? GitLab allows you to do that. Anyway, sorry, deviation. Okay, let's talk about it step by step. So this is kind of the, right, you name almost all of it, right? This is what we want. And I just wanted to make sure that, again, if you don't want something, just don't build it, right? Like in this specific example of this wearable device, you might not need a file system. Just go without it. It's much easier, faster, easier to maintain. Let's build it later, right? If the need comes. So think of an operating system as of something useful, which will provide some useful functionality, right? And minimal as well. It's again easier to maintain this way. Okay, so let's just go over whatever we just named step by step. I just like understand that we understand these things together. Okay, so we have this main, right? We said, as I was saying, we wanted to run it. We figure out that if we read the CPU manual, the CPU probably comes with a bit of firmware, like which is a software which is written by the CPU developers, which will maybe initialize internals of the CPU, do a lot of like unbelievably complicated, incomprehensible stuff, in case of Intel at least, which no one else understands besides Intel, but then eventually gets ready to run at address, let's say 0 or 55 or something like that, right? And this is where we're gonna compile our main program, link it. Again, remember, bare metal, so no libraries, nothing. Everything what you want to use, you have to build yourself, right? But essentially, it's going to jump to the entry point of the program. Okay, and as I said, that's your OS. Maybe you don't want anything else. Maybe just, I mean, I've been on a projects in which OS is this, and then you just read a sensor and count something. I don't know, count, let's say, if it's a machine which count bills, then it just does it. That's nothing else. And you don't care about timers. You don't care about anything else. That's good enough. That's what you want. Just sell it at this point. But maybe, as you say, okay, you at least for debugging purposes, you say, I want to print something maybe on a serial line or maybe on something. So I want to have a function which is called the printf, which allows me to print a string. Internally, again, you read this CPU manual and say, okay, what do I have to do? What kind of like values and where I have to write to make sure that something shows up on the screen? And you say, you code it. And maybe along with a serial line, you have something like a screen, which let's imagine I'll call a VGA. And the way it works, just again, I wanted to do this detour to make sure that we understand what these devices are, right? So up until now, we just talked about memory and the CPU, right? So this connection. Do we understand how we access devices in general? Like imagine you have a VGA screen. What does it mean to access a VGA or print something on a VGA? So how does it work?
Use like a shared.
Correct. We use a region of a shared memory space. And I'm not exactly sure, maybe you're talking about compositor, but I'm talking about a frame buffer. So a frame buffer is just a region of memory, somewhere here, of some magic addresses on which the VGA manufacturers and the operating system designers agree. And the way it works is that those buses So I don't have a VGA device here, right? But imagine I have. So imagine there is this PCI bus, which is connected to the CPU. Think of it as a network. So in a modern machine, PCI bus is more like a computer network. Like it has hubs and stuff, like, and the packets can be delivered out of order. So essentially this thing can like this bus, it sends packets back and forth. And imagine one of the devices, like which is the VGA, is connected here on the PCI bus, right? And on the other end of it, there will be like a VGA cable or HDMI cable, and it will really be connected to like a screen which you can see with your eyes, right? So this piece of hardware which sits here just constantly pulls this region of memory and says, okay, whatever I see, if I see zeros there, maybe I will put black dots on the screen. The moment you write a 1 into one of those elements, it maybe put something else on the screen, right? And a protocol can differ. Like there might be a simple protocol where it allows you to put a number and it will interpret it and put a shape over letter H, for example, for the word hello, right on the screen. But maybe different. It might be like have an encoding where you put like 4 values and those means colors, and it will just put a dot of a specific color on the screen, right? So and this idea is clear, so that devices sit on a different bus. They typically have access to memory bypassing the CPU, and this is called direct memory access, right? This bus just implements a protocol which allows a device to read this memory, and vice versa. When you, for example, like in case of a frame buffer, you just write into this memory as a regular memory instruction, but some CPU has this functionality which can convert some of those memory writes into transactions on this PCI bus. So it has a logic and says, if your write is going into a specific region, it will be sent on a bus to a specific device, right? But that's the interface, right? And you say, look, I got it. So I mean, the details are hard, but they're just like lots of documentation, which you have to get through it. Some people can do it fast, some need more time. But at a high level, the idea is very, very simple. That's the idea, right? And so you say, look, I might have this VGA device and I have a serial line. And so like I will write this code which abstracts it these 2 devices behind a single printf function. And you say if VGA is enabled, I will move into the memory of a frame buffer and it will show up on a screen. And if it's a serial line, I will like do a different instruction. In this case, it's an out instruction, which it just yet another way to communicate with this bus, right? And this thing which you put like this printf, you abstract it and call it, okay, that will be my console driver, which will print something on the screen. And if you have a keyboard driver, same idea, you press a keyboard and it shows up somewhere on the CPU, it will like, you can interact with this system, right? And you say that this is my device driver. And again, as I was saying, sometimes you don't need anything else. Like in case of Adreno, the way these packages came, this UV sensor and the humidity sensor, they were just coming with those drivers, and I could just link my main program against them and really just say, read a number. And I was given a number which was representing a UV value, whichever they measure. Internally, they probably calibrate the sensor, do whatever conversions they need to do, right? But for me as a high-level user, it's all hidden in this device driver, right? And the same for disk SATA interfaces, so serial ATA. It's like just the standard, the protocol for accessing the spinning drives, NVMe, which are solid-state disk drives, which we all have now in our computers, because no one even buys a computer. You can even buy one with a spinning disk. Network interfaces, kind of similar story here. It just might be the protocol here might be slightly different. So maybe this network interface will be using like a couple of queues, which will be allocated in this memory, and you will be putting those network packets in those queues, and once in a while, device will kick in and process them, and that's done asynchronously just to increase the throughput of this device, because they run at like really they run at a speed of like 40 Gbps. If you're sending 1 kilobyte packets, you roughly have, I would say, at 10, you have, I would say, 2000 cycles. At 40, you then will have 250 cycles. So not a lot of CPU cycles to even process a packet. So you have to batch them, right? Okay, so I thought I had a question in the audience, no? No, all good? Okay, so this yellow part, which is here at the bottom, right? I will call it an operating system kernel. And this green part will be your user process. This is your main. And those libraries and whatever else we're going to be doing here will be sitting in a kernel. And I will be using this term kernel and process, right? So, and it gradually will become clear what is what. But right now, just like, you know my diagrams later in the class, the kernel, the operating system kernel will be yellow, and the user will be something green, blue, something like that, right? So just make sure that there is this distinction. And typically, you probably know that, and that you cannot just call the kernel. You will have to invoke a system call. But in this specific example, when we're building our wearable device, it's just fine. I just link against those libraries and I call them as functions. And it's totally fine. There is one problem here. There is no isolation between the user and the kernel. So if you have a stray pointer in your C code, you can accidentally overwrite memory of this console driver, and then the system hangs in some unpredictable manner, right? Sometimes if it's if it's a car, it runs into a wall. If it's your wearable, it just shows you, wow, cannot connect, right? Well, happens. So it's ideally you have to put some isolation here. We'll talk about how to do it. But so far, this is the beginnings of this. This is, I can call it an operating system. This is Adreno. I can call, maybe you don't want to call Adreno an operating system, but you can. Okay, so device drivers. Like the high level readout is operating system kernel at this point is just like a library which provides useful functionality to you, like printf, maybe allocate memory, maybe even start a new process if you have a logic for that, right? Then you said, okay, we want to run two programs, right? So my media playing application will play a movie on my screen, and my sensor reading program, which is blue, for example, will read the sensor over and over. How do you think we can do it? So what needs to happen for this to work? In terms of, imagine I assign you an assignment in this, and you program against this yellow piece, which will already somehow load in memory. But what do we need to do in this yellow piece to implement this? At a high level, correct. But you can even do it simpler. Imagine you don't even have a timer first. You just say, I will write my programs in such a manner that they will have this yield function, which like it's a goodwill, like, but let's imagine we're all cooperative and we write this function and it yields and executes something in the yellow kernel and then saves and restores the context of this green program and then jumps into a blue one. Imagine just we forget about the timer for a second. Timer is the next step, next slide. But what do we have to do with this save and restore? What does it mean to save a execution of a program and then come back to it?
So like all the registers that you have in your CPU, just put that in memory.
Right, correct. So you really like remember that the system is kind of flat. Like it just has instruction pointer, execute instruction by instruction, and updates the values in registers and writes something in memory, right? So if you say, well, I want to save the state of the program, you literally just have to save this program pointer and the values in register, right? And then you can come back later to them, like an hour later, restore the program pointer, and the CPU will continue executing this green program from that instruction, right? I mean, that's cool. So did anyone ever did something like that? That one person. So what was your project? Tell us.
I like to
Emulation. Okay, cool, but we're all gonna do it later, but or see how it works. But at a high level, is it clear, this high level insight?
When I do some large scale machine learning training, I also need to do something similar to this. That means try point.
Right. So what you're talking about, imagine you have, like you mentioned machine learning, but imagine we just compute something on a cluster of machines, maybe dynamic molecular simulations, how molecules are moving and affecting each other in space. Just figure out some kind of a protein folding, how the proteins like fold. And we say, look, we're going to run it for a month. There's a huge chance that the system will fail, right? Maybe one of these machines on which we're running will just like do something weird, or maybe we'll lose power. And so what those people are doing, they are checkpointing the execution periodically in order to like come back to the most recent checkpoint. So it's a similar idea, but here it's a little bit simpler because you really just have to save the registers and you assume that the machine will not crash. Although there are operating systems which don't have this assumption, like extremely like, what is it? Mission critical systems, they might checkpoint themselves to be able to restart and go from the most recent checkpoint. Wow, maybe you have a power failure, like hardware error, or like really hardware malfunction, or maybe even software, but then it's trickier to recover. Correct. Right. That's a very good question, by the way. Sorry, I didn't mention. But what your classmate is saying is that do this program have separate stacks? They do. So when you start main, like imagine you have some logic which starts the main somewhere here in this yellow part. When you jump to main, before doing that, you allocate a stack for this main, right? Because this main will have some local variables. Well, local variables here, like and that's my move to Mac is not really smooth with PowerPoint, but essentially, and they will be allocated on this stack, right? And when you jump into this main, you will allocate a stack for this main as well. And let me just take it one step further. You probably heard the word process and you heard the word thread, right? So each thread of execution will have its own stack, even if they are running within the same green process, right?
Keep track of which process.
Correct. So let me get to it in a second, but you're right. So those address spaces like green and blue they consist of a stack, the code of the program, which is called text, and the heap, right? And they each will have a heap, right? But again, we just have to get to the point where we say, look, by the way, we have one single physical memory. There is a single DRAM chip which we purchased, right? And we somehow have to share this memory between multiple instances of multiple programs. Let's get to it in a second. But what I wanted to explain here is essentially this idea that you can save and restore state of a CPU, right? Of a program. And they will be taking turns. And this is like when I run this laptop, if I do, everyone sees my email, which is probably, yeah, spooky. So these are just the bash shells which I own and run in this. But if I do minus, I say all from all users. Let me show like this. Really? What is this? No X on Unix? No. I need more experience with Mac apparently. But my goal was to show, how can I, let's see, top. Like another tool, top, shows me everything what is running in the system. And there are like roughly 200 things are running. My GUI manager, Zoom, whatnot, right? So probably Zoom is like not surprisingly involved because it uses all my CPU to record. What else? Firefox is here, my favorite guy, because he's all my memory and stuff like that, right? But so a lot of things are running, right? But to us, they look like it's kind of smooth, right? Because they take turns so fast that as humans, we cannot notice unless you play video games where it's like 100 hertz and you have to react to bullets and everything. Then you develop this skill where you have to really be, you see the delay at some point or you lose. And that's what I was saying. Like it's similar to car sharing. So there is a single physical CPU, single physical fetch, decode, execute loop, and the programs just take turn on this CPU, right? So one runs, then yields to operating system, launches, operating system picks another program to run, runs that program, then that one yields to the operating system again. This is called cooperative multitasking. Cooperative because you rely on this yield to get control back to the operating system. Of course, you say, look, but that's not realistic. You know, my web page, which I open, will never give back the yield. I mean, the web browser might, because internally, but like direct, like imagine you're writing a program which does an infinite loop, right? And it runs forever. And at this point, you say, look, I need something else. And this is what you mentioned. You mentioned interrupts or exceptions. And I said, I have a couple of I have a slide about the state, but you already named it. So it's registers and roughly some metadata about the process, like its layout of its heap, layout of the stack. And it's already part of the kernel because you maintain this metadata in a kernel. So you don't really have to save much in a kernel. So just think of saving the registers as the way to implement the context switch, right? Yeah. So another question. So we got the CPU, but someone was asking what happens. How do we essentially keep track of which program has its own? Okay, where is the heap of which program in real physical memory, right? So how do we do that? Do we you have an idea? Correct. So what I wanted to say, okay, I just wanted to emphasize the fact that physically there is one DRAM chip, right? It is addressable from address 0 to address whatever, 32 gigabytes, for example, right? You bought it, you put it in your board, CPU can talk to it, right? Now you have options. You can say, look, but really you want to have multiple heaps, multiple stacks because you're running multiple programs. You can say, well, maybe I will be doing something similar what I do with a CPU. You will be copying in and out this memory. Like, for example, either you can copy the entire thing given to disk, or maybe copy it into a region of memory of this DRAM bank, which no one else uses, right? So it's kind of a feasible idea. So it's say, look, I can copy it out, I can copy it in, it will continue running, right? So what will be wrong with this idea, or what is wrong with this idea? Like with the CPU, we save the registers, we restore the registers. Save the registers, restore the registers. You can do the same with memory. I just want to understand that we all understand that it's possible. But what is wrong with this? It's very, very slow because imagine you're running a program which is like a couple of gigabytes. You probably can copy a page of memory, which is I use the term page, sorry. So it's a region of memory which is 4096 bytes in roughly 250 cycles. Now multiply it by a gigabyte. Like, what is that like? If it's by a million, right? If you want like 4 gigabytes or a quarter of a million, right? So it's a lot of cycles to copy in and out, right? So as a human, you will notice, especially if you're a gamer or even like as a regular human, you will notice, right? Yeah. You will be just sitting there. But when I was again, your age, badly wanted to play video games, right? And I had a machine which had maybe like 32 megabytes of memory, DRAM, and a disk. Well, there is this idea that you can swap memory to disk, and no matter how long it takes, you still play just because there is no other way. But this is not what is done, right? So we're not copying memory in and out. Instead, there are multiple ways to do it, but modern CPUs came up with this idea that you can virtualize memory. And at a high level, it looks like this. So you have a single bank of memory here at the bottom. This is your physical DRAM chip. But CPU has special metadata, what is called a page table, which allows it to expose a virtual address space to each program. So what it means is that when you have something like an instruction here, which I will use a move instruction I mean, maybe let's better use something like store instruction, right? So, like what assembly do you guys know? Like MIPS, but probably everyone was in one of the architecture classes has a MIPS, right? Assembly, knows MIPS assembly, which is kind of like RISC. So I will use x86, but I will introduce it later in the class. So today we're gonna use MIPS. So when you do something like a load, and imagine there is some kind of an address, and I put, man, really like, I wanted to put 0 here, and I cannot put X. Let me start over again. So probably have to change my slide deck to something. I will be very gentle. Almost. And I load into into register 1, right? So this instruction load in my whatever encoding, which doesn't exist, takes a value from address 0 and puts it into the register 1, right? But in practice, what happens is that this instruction doesn't access address 0 here in physical memory. The CPU internally says, okay, I will access some other address. And what I will be doing, I will essentially pretend that I'm accessing this address in this address space. But I will go through those page tables, and really this something what is called a page, this region of memory is mapped here in physical memory. I will really read address from here, right? And this way, it's kind of like virtual offices, if you like. You say, look, today your company is in the office 1 or 0, and you go to some room 10, like whatever. Question.
Does the OS control?
That's a good question. So look, when the CPUs are designed in such a manner that most, not all, but most parts of the CPU are kind of open to the OS. So when OS boots, it typically has control over everything. I say almost because the CPU designers play tricks on us and they didn't open up the CPUs completely. And some things are actually running and are hidden from you. And I will explain later on what these are. But the page tables are specifically designed in such a manner that the operating system sets them up for each process to essentially say, this green guy will have address 0, which is mapped here, and the yellow guy will have address 0, which will be mapped somewhere here, right? And this way, they all have an illusion of its own private address space. By the way, they can't even access the address of like memory of each other, just because if OS configures those regions are called pages. If OS configures them in such a way that they don't overlap, there is no way for a green one to access those yellow pages. Or the OS can configure them in such a manner that they are shared to enable like communication between processes, right? Okay, so this is virtualization of memory. And this is the way how it's done today, but it's not the only way to do it. So you can come up with different tricks. You can actually get away without the page tables. There are different isolation mechanisms which you can use, and you can even just use the software, like no hardware support whatsoever. If you heard of this term, which is called WASM, right? Back in the days, there was NACL. Google NACL is essentially the idea that you can take a Quake game, compile it, and run it in a web browser. So Quake is written in C++, but somehow you can do a compilation trick on it, like kind of inserting checks in front of every load and store, and you can safely run it in a web browser. Big breakthrough during my time, when I was still interested in Quake. But today, this idea is taken forward, and the standard which came out of it is called WASM. So essentially, WebAssembly, you can take a C program, compiler does some tricks, I will explain later what, and you can place them in the kind of like a green address space and a yellow address space, and no page tables are required because you're still running it within the same web browser, right? So you don't always need page tables, but like this idea of virtualizing memory is the core idea, but you can build it differently. So I had a question somewhere in the back. All good? Okay, we got it. So now we just essentially say there's one physical memory and multiple processes will use it. And at this point, later in the class, what I want to say is the following. So I keep saying process. I never really defined it. At some point, the definition will be, again, kind of verbatim. There will be a data structure in our x86 kernel, which will be called proc or process. And you will see that this is really a process. So if anyone on a job interview will ask, what is a process? You can roughly remember each field of this data structure, and you will give a very in-depth answer to like, it's quite good. And one of the main fields in this data structure, if you can guess, obviously, right, it will be a pointer to a page table, which implements an address space for this process. There will be also like a pointer to the file descriptor table, name of a process, stuff like that, right? But this is, when I say a process, I often can mean, essentially I say like, it's something what has an address space, right? And so we run multiple, like it will have its own main function, which we compile, load it in memory, somehow set it up, and it's running, and we switch between them, right? Okay, so yeah, operating system will have a part which will virtualize memory. Now, someone mentioned, okay, what about, like again, I mentioned that, but you also mentioned it, that if one of these programs essentially fails to release the CPU, fails to yield, I mean, you can say, okay, like, why am I even talking about yield? But when I was young, like again, your age, there were operating systems which were relying on yield. I will surprise you that one of them was Windows. I think it was cooperative multitasking back then. Later on, they moved to Windows. They call it, I think, Win32 or Windows XP or something like that. And that one had a preemptive multitasking. But originally, again, maybe even macOS had cooperative multitasking at some point. But what I mean here is the following: like, imagine a program which runs something forever, adds the numbers. Like maybe you're crunching Bitcoins, like like your goal is to keep crunching, not to ever exit it, right? But no other programs will ever run unless there is a mechanism which allows the operating system kernel to stay in control. And this mechanism is called a timer. So the timer is actually a device. So it's a physical, like some kind of logic on a CPU. There's physics behind it, whatever. Periodically, it can issue a signal. I used to know the physics, and now I don't remember it. But the frequency changes with temperature. That's why you can, sorry again for this. That's why I can fingerprint your machine. So each of your machines will have a slightly different skew, and let the clock will be deviating from the real time, and I can say, okay, this person was that, and this one was that, just because your timers are slightly different. But the idea is the following. So the timer, remembering that my fetch, decode, execute loop, at the top, there was a block which says, okay, did something bad happen? And if nothing happened, we went and fetched the instruction. But if exception happened, the CPU internally actually redirects control. So it says, okay, I have a table of saved instruction pointers, which I have to execute on specific exceptions. And one of them will be timer. It's not, the table is configured by the operating system. And essentially when it sees the senses that the hardware send the timer event, it just redirects control to that instruction pointer, which corresponds to the timer interrupt handler. Again, later in the class, we'll walk through this step by step, understand how exception works, how control gets shifted to the timer interrupt. But conceptually, it's relatively simple, right? CPU, instead of executing the next instruction, says, okay, I send something, I will go look up a table. The table is saved in memory, configured by the operating system, and I will jump to that address. Maybe saving some state in order, at least it has to save the old instruction pointer. So after you're done with the timer, you can go back and continue executing the program, right? It's kind of natural idea, but everything else maybe gets saved in the timer handler itself. Questions?
You said the timer actually has a physical hardware.
Yeah.
So I want to ask if I have many CPUs, there should be only one timer.
No. No, first of all, there are like multiple timers in modern CPUs, but typically each core will have its own timer because each core will be running the same. Like I put one core, but the second core will be sitting here and will be running its own process. Like it will have its own instruction pointer and it will have its own timer, which will allow that core to make a decision to.
So every core has its own timer.
Right.
But so all the timers does not have to synchronize each other.
No, and that's interesting. And that's interesting when it becomes, when you want to measure time across two cores, it's a
Yeah.
little bit of a challenge, to be honest,
That's
because
true.
they actually, like you don't have a good reference of time, and then you
Yeah.
play a protocol to synchronize them. And so the time on each core is slightly different, actually. Like that's a challenge.
So actually that's kind of like not absolutely.
Right.
Okay, I see.
So we can talk a little bit more about time later, but it's a tricky concept, as I said. So if you really rely on very precise measurements in the order of nanoseconds, it's not so easy, actually. Okay, but we got the idea. So we got why the timers are needed. Again, remember, in my Arduino chip, I didn't need any timers. I was in one main loop. Well, no need for a timer, but if you have a timer, you have this flexibility of switching between processes and making a choice which one can run next, right? And account for how long each one runs, right? And then enforce some kind of fairness. And that's called scheduling. So essentially, discipline inside this operating system kernel, which decides what is fair and which process to run. I'm not an expert, but it's very easy at the naive level. You just say, let's take turns. Imagine we have a bike. We're all kids. We want to ride this new bike. We agreed that we all take a turn of 5 minutes on a bike, right? We line up and just, I take a turn, you take a turn. And then when I'm at the beginning of the line again, I take a turn, right? Very easy. It's called round robin scheduling. It gets a little bit complicated when my mom says, okay, go and take lunch. And I disappear for half an hour. I come back and say, look, I missed 2 turns. Is it fair for me to run for 10 minutes now, for 15 minutes? You have to decide, right? At this point, you have, like, you as a designer of the operating system will have to decide what is fair. And usually it's optimized for either performance or user experience. But there is not a very good answer yet for, like, the scheduling policies are always falling apart. Correct. Yeah. Right. So people probably don't do it on purpose while being good citizens, but attackers do this. So attackers exploit those vulnerabilities to observe specific cache patterns. Those are called side channel attacks. And just essentially to read the values from, we will talk in a second about isolation. Those page tables do isolate memory of each process. Surprisingly, on modern machines, an attacker can read memory of another process by observing the cache behavior, right? So something what is called like meltdown and Spectre attacks, and later on, general like idea of side channel attacks. So people do this, but typically, you know, the ecosystem is controlled tightly enough that, you know, you will get kicked out if you like optimize your programs for the use. But actually, I mean, it's a long discussion. So maybe it happens in real life.
Do you know if there's any scheduling that like associate each process?
Correct, right. So absolutely. And again, in my analogy with a bike sharing, if I own the bike, maybe I will say I have a higher priority. Maybe I will write it as like first, I will always write it first when I'm around. And maybe I will write it instead of 5 minutes, I will write it for 10. And we might agree that it's actually fair, right? I want to ask a question. So I end at 30 minutes, right? Not 20. I still have 10 minutes. Okay, cool. Right. So these policies are there. Priorities are there. Priorities make a lot of sense in case of embedded systems. Imagine you have a car. You have an entertainment system which shows a movie to you, maybe, or a map or something, right? But there is a set of processes which, like a set of tasks which are responsible for controlling the wheels, for example. They always have to run the moment they need to run, right? And they will have a higher priority and will run first. Actually, as I said, I'll come back to it, but cars is like a fascinating domain for operating systems because, as I said, it used to be that they ran 100 different microcontrollers and then they run one board. And I met a guy who is a professor at, I think, Boston University, and he works with a startup which builds a very cool, like, you definitely know the car. I think it's called Draco or something like that. And it's a super like high-end racing car or whatever, muscle car. And his software, which he builds, his operating system stack, runs on that car, and he drives that car. Oh. Well, and when I show it to my students, they are super jealous because the car apparently costs like a ton of money. And but yeah, so a lot of scheduling, like in that domain, this priorities and enforcement of fairness becomes the ultimate goal because the entertainment system doesn't have to run until everything else finishes. Okay, so a couple of things, like again, as I was saying, originally Arduino, couple of sensors. We don't care about isolating one sensor from another, but really in a real world where those programs come from third-party vendors, especially when we run them in a web browser, they might be malicious. They might try to read your SSH keys, your bank account, stuff like that, right? And so operating system really has to enforce this isolation between processes themselves and between the yellow part, which is the kernel, and the process, right? Because if you get access to the yellow part, you own the entire machine because you can control the page tables, remap the memory, access everything, right? So, and again, this is an abstraction of this. If there is no isolation, it looks like an open space office. Someone will be stealing your pencils from you. But operating systems today, typically, they lock everyone in the room, and you can only exit and enter through a TSA-like style controlled entry point, right? I mean, people were very optimistic about isolation, was that it was solved, but in practice, it's not. And there are multiple ways to attack it and essentially see through the walls of those offices and actually escape. So, which is, again, it's a discipline which pays, right? These days, security is paying. And so by looking at the code of the operating system, which we're gonna be studying in this class, you will get a better handle of what it means to attack, right? So we already talked that, okay, each process has an address space, and in a simple case, the isolation is solved by simply giving each process its own page table. Like in this example, the yellow one, the green one has a page table, process 1, and the pink one has a page table, process 2, and the operating system just configures those page tables in such a manner that in physical memory, the green pages don't overlap with pink ones. And so no matter which address the pink process tries to access, 0, 1, 2, they all fall in physical memory on pages which are disjoint from the pages of other processes, right?
Yeah, I noticed you said in the prog structure, we have a page table pointer for each process. What I'm thinking is we also have a user space and kernel space. So that does it mean will they share the same page table or?
Correct. So so the question was whether the user part, which is green, and a yellow, which I show here at the top, whether they share. So I have the green part and a yellow part here, right? So sorry, maybe wrong drawing. Almost there. Right? Do they share the same page table? In our case, in case of x86, they do, right? It's easier to implement a system call because you don't have to switch the page table when you call the kernel, because this page table will have a special bit saying, while running in user space, you cannot access the yellow part of the page table. And when you do a system call, you essentially change the privilege level and this bit becomes irrelevant. And then the code can access the part of the kernel. You enter the kernel, you can access it, right? Modern operating systems generally use the same technique. The page table user and kernel part of a process uses the same page table. That was the case before this meltdown attack. Meltdown was using a vulnerability in a CPU, which allowed the green part to read memory of the yellow part through like a bug in how the CPUs execute instructions out of order in a speculative manner, right? And then people said, okay, by the way, we're going to introduce this isolation mechanism to prevent this attack. And we essentially do not allow the yellow and the green part to share the page table. And this was guarding against this attack. The technique was called KPTI, kernel page table isolation. And it was for a while, let's say for 3-4 years, you can see that, okay, machines, so like systems like Linux were implementing this technique. Then thanks God, meltdown was supposedly fixed, or most of the versions were fixed in hardware. And so you don't need to do this trick again, because the trick was really slow, because switching a page table is a slow operation. And so then your system calls, and if you do a lot of file reads and writes, and each system call requires, when you do a write, you enter a kernel, it slows you down, right? So it went away. So right now, again, the page table is shared. And this is how it will be in x86, in a version of x86 which we are using. And the MIT people actually moved away in their RISC one, they use a separate page table. And that's one of the reasons I didn't want to move, because it complicates things. And I don't think it's relevant, because the meltdown attacks have to be fixed in hardware and will be fixed. Okay. And of course, since I said everything is isolated, you cannot simply invoke functions. So you really need to build those mechanisms. And you all heard about system calls. So system calls are essentially a way to invoke the kernel from user space. And inter-process communication mechanisms, or IPC, something like we will take a look at a pipe, is a mechanism which allows you to pass data from one process to another, right? So it's kind of natural. You isolate first and then do a controlled entry. Okay. I mentioned that we will talk about files and network. Files, essentially, just that I have 2 minutes and I don't want to like finish next time. So files, essentially, idea that you can abstract the disk space, which is kind of like a memory space, starts from 0, ends at whatever, some megabytes or gigabytes or terabytes now. But as I was saying in my anecdote, like it's really hard to understand whether 0 is already taken or maybe 1 is taken, and just naming block 1, block 0 is cumbersome. And what if file is growing and one file is 1 block and another file is 10 blocks, right? So file system does it for you, right? So essentially, it abstracts this idea that a write to a disk is just a block number with a piece of data behind the interface, which shows you, let me show you what it shows you. You say, I will open a file like this context.txt. Operating system will give me something what is called a file descriptor, and then I can use this file descriptor to write into a file. And I can use like formatting functions, but really internally it will make sure that, you know, if you need more disk blocks allocated underneath, it will allocate them. It will make sure that if you crash during the write, when you reboot, the file will be in something what is called consistent state and stuff like that, right? So, and okay, almost there. So file system, again, part of the operating system kernel, almost the last slide here. So this is roughly how any modern kernel, which we're running, Android, which uses Linux, Linux itself, Mac OS and Windows, look like internally, right? So they run applications or processes at the very top. They rely on system libraries like libc and whatnot on Windows, right? To essentially provide local memory management inside the process, but also provide the system call interface, the interface which allows the user part to invoke the yellow part, the kernel. And inside the kernel, we will see essentially bits of software which are responsible for virtualization of memory. We know what it is. There will be a timer, interrupt handler. There will be a scheduler which picks the next program to run. There will be software stacks for the file systems, right? And access to storage, software stacks to send packets over the network like TCP/IP. And that's essentially the kernel. The full feature kernel today essentially implements all this functionality, but you never have to do, unless you need to do it, you don't have to, right? But typically you converge, because sooner or later, and even x86 implements most of it, it just misses the network stack. So, but it has a file system stack, scheduler, virtual memory, stuff like that, right? Okay, so this is kind of the end of the introduction. So next time we will start on like moving slowly. We will start on what's inside the process, how you can link and load, essentially. Remember, get to the point where you can run the main in a specific address, and then we will move forward how we boot into the system and how we build those individual components. Okay, thank you. Then I will see you next week.
So the structure is a monolithic kernel.
Correct.
As that, no, the Windows does not. The Windows use microkernel.
Right, so there is but I think it still sits in a shared address space. Meaning that it's kind of a microkernel. Stop recording.
How about Mac?